I will talk about asymptotic efficiency of a one regularized model average and composite M estimators via approximate message passing in this presentation. This is a joint work with my PhD supervisor, Professor Heather Kloskens and Professor Elena Bradic from UC San Diego. Our goal is to estimate a parameter vector beta for sparse high-dimensional linear models where the number of parameters p and the sample size n follows a linear order when both n and p go to infinity. In this presentation, I will talk about how to obtain the asymptotic mean squared error um, via approximate message passing and the corresponding AMC type weight choices for the L1 regularized model average and composite M estimators. In addition, we do not require the loss functions to be differentiable. And further, I will talk about how to construct the component-wise confidence intervals and hypothesis testing. I will also showcase the quantile estimators. Um, we start from introducing the two weighted quantile estimators. The first estimator is the model averaged quantile estimator obtained by weighting case single quantile estimators. For this estimator, only the single quantile loss functions are involved. And in the left panel of the figure, I also have an example single quantile loss function. And the second estimator is a composite quantile estimator obtained by first weighting k single quantile loss functions and then perform one-time estimation in the end. In the middle and right panel of the figure, I have two example composite quantile loss functions using equal weights and unequal weights. From the expressions of these two estimators, we see that the weights are quite critical for these two estimators. So naturally, a question would be, how do we choose weights for these two estimators? We would consider the asymptotic mean squared error for these two estimators for the weight choice. So essentially what we want to achieve is to obtain the asymptotic mean squared error of the L1 regularized M estimators. However, the issue is that the AMSC expression of estimators from regularization is not obtainable. Our solution is to find a substitution with tuning parameter alpha satisfying two requirements. The first is that the difference of the substitution and estimators from regularization converges to 0. And the second requirement is that the AMSC expression of the substitution is obtainable. A possible choice of the substitution is an estimator obtained from the robust AMP algorithm. The robust AMP algorithm is an iterative algorithm consisting of 3 steps, and the iteration steps are indexed by T. I will not give details about this algorithm here, but I will talk about the links between estimators from regularization and estimators from the robust AMP algorithm here. For obtaining an estimator from regularization, we need 2 elements. The first is the convex non-differentiable loss function, which corresponds to the rescaled effective score function in a robust AMP algorithm. The second element is the L1 regularizer with tuning parameter lambda, which corresponds to the soft thresholding function in the robust AMP algorithm. And I want to note here that the argument, the estimator denoted by beta tilde in the first argument in the soft thresholding function is asymptotically normal distributed, centering at the true regression coefficient vector. And this estimator is quite critical for later deriving another estimator and for constructing the component-wise confidence intervals and hypothesis testing. From now on, we will work with estimators obtained from the robust AMP algorithm. We say at iteration step T, the model average estimator has the asymptotic mean squared error expression as a quadratic function of the weight vector with a sigma naught matrix in the middle, and we let the number of parameters p go to infinity. this quadratic expression converges almost surely to another quadratic expression of the weight vector with a limiting matrix sigma in the middle. The variable B naught represents the limit of the regression coefficients, and the big chunk of the self-thresholding function here corresponds to the regularized estimator beta hat. And the argument in the self-thresholding function, which is a convolution of the variable B naught and another standard normal distributed variable Z, corresponds to the estimator beta tilde and the self-thresholding function in the robust AMP algorithm. I also want to note here that the composite M estimator is a special case. The AMSC type weight choice is derived by minimizing the quadratic asymptotic mean squared error expression. We note here that the AMSC type weight choice is determined by the sigma matrix, which contains information of the true regression coefficients. So for practical use, we need to derive an estimator of the sigma matrix. Motivated by the asymptotic normality of the beta tilde estimator, we derive a Stein type estimator denoted by sigma hat naught, of which the expression can be found at the bottom of the slide. So also motivated by the asymptotic normality of the beta tilde estimator, we're able to construct a component-wise confidence intervals and hypothesis testing. We start from the component-wise confidence intervals. Motivated by the asymptotic normality of the single estimators beta tilde k, we are able to obtain the asymptotic normality of the model average version of the beta tilde estimator. This beta tilde MA estimator centers at the true regression coefficients with a standard deviation zeta bar. And by rewriting the asymptotic normality of the beta tilde MA estimator, the model average version of the beta tilde estimator, we are able to obtain, we're able to define another variable B tilde, which follows a standard normal distribution. The component-wise confidence interval for the confidence level 1 minus alpha can be constructed using model average version of the beta tilde estimator and the standard normal distribution, and an estimator of the standard deviation denoted by zeta bar emp. We are also interested in the hypothesis testing at significance level alpha. We start from the individual hypothesis testing. We want to test if the J's component is equal to some value beta naught versus alternative, that is beta J is not equal to this value. In the first step, we construct the test statistic, which is defined as the difference of the model average version of the beta tilde estimator and the value that we want to test, scaled by the estimator of the standard deviation zeta bar emp. In the second step, we calculate the p-value using the standard normal distribution evaluated at the absolute value of the test statistic. A null hypothesis is rejected if the calculated p-value is less than or equal to the significance level alpha. We are also interested in multiple hypothesis testing. We want to test a family of hypotheses. This multiple testing is based on a Holm-Baffaroni adjustment. In the first step, we calculate the p-values for the individual hypothesis. In the second step, we sort the p-values in ascending order. And in the third step, we adjust the significance levels for the individual tests. In the last step, we reject the null hypothesis if the calculated p-values are less than or equal to the adjusted significance levels. We conclude this presentation here. We have presented the AMSE expressions of the L1 regularized model averaged and composite M estimators via the robust AMP algorithm, and later we derived the corresponding AMSE type weight choices by minimizing the AMSE expression of the two estimators. And in the end, we have seen the confidence intervals and hypothesis testing based on the model average version of the beta tilde estimator from the robust AMP algorithm. And this talk is based on this paper published in the Electronic Journal of Statistics.